So we have a rod of length, let's say here it is 20 centimeter. For convenience, we are going to derive the equation. So let's take the length as L. We have a rod of length L, in which one end of the rod is connected to a spring having spring constant K, and we need to find the equation of motion of this rod. And before that, we need to find the torque acting on the rod. So there are two forces which act on this rod. One is the spring force. See, there is a force along this direction, which is because of the motion of the spring, or the spring is having a spring constant K. So definitely due to some extension there is a force. And we know from Hooke's law this force is equal to minus K into X, where K is the spring constant and X is the extension. Now we need to find the torque acting due to this force. So this is the line of action of the force, that is this one. And we have the axle here. So the perpendicular distance between this line of action of force and the axle will be this one. And we can name this as, let's say this point is A. We can call this point B. Let's take this point C. So first we need to find the torque acting. This one is 90 degree. This is 90. So let's take the torque due to the spring force about, we have this point A, axle at the point A. So torque always acts about a point. So torque due to spring force about A equal to this force. We can represent that as torque due to spring force as tau S is equal to force F into this distance AB. Force into this distance AB. So we need to find the distance, and before that we can draw an axle or an axis for this rod. This is the axis, and it is given that this axis of this rod is making an angle of theta with the vertical. So let me draw this triangle here for convenience, that is ABC, ABC. The triangle is like this. It's a right triangle. A, B, C, here it is 90, and we know this angle is theta. This AC is L. We need to find first AB. In order to find AB, it's better we take the cos. Cos theta, cos of this angle theta is equal to adjacent side by hypotenuse AC. That will give cos theta is equal to AB, we don't know, let's write it as AB itself, and AC is L. And we also know this angle is very small. Theta is approximately 0. It's not 0, but its value is very much close to 0. So cos theta basically means cos of 0. We know cos 0 is 1, approximately equal to cos 0. Cos 0 is 1. So we can put 1 instead of cos theta. So 1 equal to AB upon L, which means the length AB is almost equal to L. So this equation, let's call this equation number 1. So the torque acting due to the spring force tau S will be F into L. Clear? And we know tau S is equal to, we know force F is equal to minus Kx into L. See, this is the force. Force is equal to minus kx. And also this length BC is the x value of x. This will be the small extension made on the spring. So let's call this as equation number 2, and we need to find an expression for x. For that, let us consider the sine theta. We know sine theta equal to opposite side, which is equal to BC upon hypotenuse AC. Again, for small values of theta, sine theta is approximately equal to theta itself for small values of angle theta. So this will become, instead of sine theta, I can put theta is equal to BC is x, AC is equal to L, implies x is equal to theta L. So I can put this value in the equation 2. So we have torque due to the spring force equal to minus k theta L, x is theta L, into L, implies the spring force tau s is equal to minus k L square theta. Okay, this is the torque due to spring force. Now, let me erase this. Now, the next force acting on this rod will be the mass of the rod itself. We know this will be the center of the rod, and there will be weight is vertically acting downward. We can call W is equal to mg, m into g. This is the weight acting weight of the rod, and this will be the line of action of the weight, and the distance from the axle to the line of action of the weight will be this one. When I join this line and I call this as ABC, let's call DE. This length, if this is A dash, we know A dash will be equal to DE. So now the torque due to weight of the rod about the point about A will be, let's represent that as torque due to weight as tau W is equal to weight of the body W times the distance A dash, or we can put DE, since A dash and DE are the same. Now we need to find the value of DE. For that, let us consider this triangle ADE. ADE. Again, this angle is 90, but this length AE, you know, it will be half the length of the rod, because E will be the exact center of AC. And we know we can take this is theta. Now we can take sine theta. Sine theta will be opposite DE upon the hypotenuse AE. That is sine theta. We can put it as theta itself, because the theta is very small. DE is, we don't know, DE divided by AE is L by 2, which will give DE is equal to, let me erase this, DE is equal to theta into L by 2, or you can write theta L by 2. So this is the expression for DE. Now we have tau W, torque due to the weight tau W is equal to W. See, W is, weight is in the downward direction. It is in the downward direction. So you have to put a negative sign. So it is W is equal to minus mg. Here it is actually minus mg into dE. You can put dE as theta L divided by 2. Now you can rearrange the quantities and you can write this as mg L by 2 into theta. So this is the expression for the torque due to weight. Now we have two torques, torque due to spring force and torque due to weight. Now we can write the total torque or the net torque acting on the rod. Net torque on the rod, you can call that as sigma tau, or that is the net torque, will be the sum of these two torques, tau s plus tau w. So that is sigma tau is equal to tau s. You can write that as minus k L square theta plus minus mg L by 2 theta. Or you can take the negative sign outside. So the net torque acting will be tau is equal to minus of k L square theta, or you can take the theta also outside, plus mg L by 2 theta. You can put the theta here also, but it's better in this way. So this is the net torque acting on the rod. Clear? Now we need to find the equation of motion of the rod, or equation of the motion of, or equation of oscillation of the rod. We know the torque acting, the net torque will always be the product of moment of inertia into alpha. Here I stands for moment of inertia of the rod, and alpha, its angular acceleration. Again, we know alpha is actually the second derivative of the angular displacement, which is d square theta by dt square. So you can write this as, this can also be written as I alpha is equal to sigma tau. So I they have given the value of I is equal to, it's actually 1 by 3 ml square. The value of I is given in the question itself. So you can write 1 by 3 ml square, that's the I, into alpha is d square theta by dt square, equal to minus k L square plus mg L by 2 into theta. You can take the values, quantities on the left side to the right. So you can write d square theta by dt square is equal to, this will move to the numerator, 3 divided by ml square, 3 divided by ml square times minus k L square plus, k L square plus mg L by 2 times theta. So d square theta by dt square is equal to, you can take the value, this 3 by ml square into the bracket. So this will be 3k L square divided by ml square plus 3 mg L divided by ml square times theta. Now you can cancel this L square and this M will get cancelled. One of the L will get cancelled. So you can write d square theta by dt square is equal to minus of 3k divided by M plus, there is only 3g left here, 3g divided by L. There's actually a 2 here, I forgot to write this 2, so there is a 2L times theta. So you can take this value, or this is the expression, you can write this way also, d square theta by dt square, taking this to the left, plus 3k divided by M plus 3g divided by 2L times theta is equal to 0. So this is the equation of motion of the rod. Clear? So when you come, now you need to find the time period of oscillation. Now when you compare it with the equation of motion or a simple harmonic motion, that is, we have the equation of SHM. SHM means simple harmonic motion. We have d square theta by dt square plus this omega square theta equal to 0. This is actually the equation of SHM. When you compare these two equations, you will understand this omega square is equal to this value 3k by M plus 3g by 2L, because the coefficient of theta in here is this one, here the coefficient of theta is omega square. So we have omega square is equal to 3k divided by M plus 3g divided by 2L. So which will give omega is equal to root of 3k divided by M plus 3g divided by 2L. So this is the expression for the angular frequency, and you know omega is actually 2 pi divided by t. Omega can be written as 2 pi divided by t, where t is the time period of oscillation. Is equal to 3k by M plus 3g upon 2L. Taking the reciprocals on both sides, you have t by 2 pi is equal to 1 divided by root of 3k by M plus 3g divided by 2L. So the final expression, that is the expression for time period t, will be 2 pi root of 3k divided by M plus 3g divided by 2L. Clear? Now there is one more question. I didn't write it on the thumbnail. The question is like this. We have the displacement, angular displacement at any instant equal to theta 0, where theta 0 is the maximum displacement, times cos omega t plus phi. Also omega is, we already found out, omega is equal to 3k by M plus 3g divided by 2L. And we know, we found out d square, the equation of the motion of the rod, d square theta by dt square is equal to minus 3k by M plus 3g by 2L times theta. The question here is, we need to check whether this displacement satisfies this equation. For that, let's call this as equation number 1. So we have theta is this one. First find the first derivative. d theta by dt will be d by dt of, or d by dt of theta 0 cos omega t plus phi. This theta 0 is a constant, you can take that out. Now the d by dt of cos omega t plus phi. Now it will be theta 0, derivative of cos is minus sine omega t plus phi. Now you have to put this omega into omega. This is according to the chain rule. So this is equal to minus omega theta 0 sine omega t plus phi. So that's our d theta first derivative. Now d square theta by dt square means we have to derive this equation again. That is d by dt of minus omega theta 0 sine omega t plus phi. Now if you again derive this equation, you will get d square theta by dt square is equal to, again this omega theta 0 is a constant, into, now let's derive sine omega t plus phi. The derivative of sine is cos omega t plus phi 0 into omega again. So d square theta by dt square is equal to minus omega square, this omega into omega is omega square, theta 0 cos omega t plus phi. Clear? Again, if you look at this equation, that is our theta, so we can write d square theta by dt square is equal to minus omega square, this one is theta. Okay. Now this is omega, we have omega square is equal to, this root will get removed, we have 3k by m plus 3g by 2l. So this is equal to d square theta by dt square equal to, instead of minus omega square, you can write 3k by m plus 3g divided by 2l times theta. Now if you compare this equation 1 and 2, they are the same. So definitely this equation or this value of the displacement satisfy the equation of motion of the rod. Clear?